All right, chapter 6. Okay, chapter 6 is exponential and logarithmic functions, but section 6.1 isn't really about exponential functions or logarithm functions, but they're kind of introducing the idea of these two functions. So keep in mind, the main point of chapter 6 is to understand the exponential function, y equals a to the x, and the inverse of that, the logarithm function, y equals log base a of x. And because these are inverse functions, the book has to introduce that concept, but they don't really have to, actually. You could talk about exponential functions and logarithm functions without this, but they're trying to introduce them together. All right. So the first thing they want to talk about is composite or composition of functions. And you have some very straightforward questions in the book on this, where they talk about, composition of functions. All right. But the basic idea is when you have two functions, f and g, you can add those functions together, you can divide them, you can multiply, you can do all the things you do with numbers, but there's one more thing that you can't do with numbers, and that is you can do the composition. And what does it mean? All right. Well, basically it means when you, f of g of x, or the composition of f and g of x, is f of g of x, meaning you're taking the argument, you're taking g of x and making it the argument of f of x, of the function f. So you're, I'll do it with my hands. You're taking one function and putting it inside another function. You can't do that with numbers. You can't take a 6 and put it inside a 4 or something. So there's no composition with numbers, but the symbol, composition of functions. Oh, they talk about domain with this, and you know, we'll unfortunately, I don't think we'll really understand. I think we'll better understand domain when we actually do a problem in this section, and we'll even understand it in the next section, section 6.2, a little better when we're doing the work. All right, so you have two functions, and let me just kind of say, so f of g of x means I'm going to take g and put it in as the argument. Maybe I should have drawn the arrow here, right? But since x only occurs one time, so this, well, it says 1, okay. F of g of 1 means, and then I'd put in a 1, but we'll just look at it. So here's the procedure. Anytime you have this composition, you will write it this way, where you take the second function, put it inside. And then you have to calculate what g of 1 is. Well, g of 1 means you put a 1 in for this function, you get 3. I did it over here. And then keep on calculating. So it's kind of just an order of operations problem from there where you're substituting. But you have to substitute in order. All of the others work pretty much the same way. This time g is the outside function and f of 1 is the argument. So it's just a long way of saying find g of 4. F of f, that's fine. F is both the outside function and the argument. And g of g. All right, so g is the outside function, g is the inside function. Gets a little more interesting when they ask us, okay, let me just say, so they're going to put an x here, leave an x here, and when they have an x in the question, the answer is going to have an x in the answer. So I just wanted you to know that what we just saw with the number here as the argument has, I don't know, kind of a pace to it, and it changes a little bit when they ask you for something with an x there. Before we get there, they're asking us not to find, well, they are asking us to find the composition of the functions. And they add this last part, and they say find the domain, or probably the better wording would be keep track of the domain. That little arrow we saw earlier, not too important, little set thing. All right. So notice how the problem was written. It says find f of g. Now they could have written it this way, and they will. All right. With the x there. All right. So they said find f of g of x. By the way, sometimes this is, I don't know, playfully read as fog, F-O-G, but it's not a full-size O. But in case you ever hear a tutor or somebody say it, a video, say fog, that's f of g of x. All right, so that's what it means. There's really can't be any question here. Why did they do this step? Because that's what f of g of x means. It means f of g of x. All right. So we're going to take g of x and put it in for the argument of f. What does f say to do to the argument? It says to square it, and then add 2 times it, and then subtract 5. So again, what I want you to think of when you see this is think of this as instructions of what to do to any argument, whether it's x or something more complicated. Take the argument, square it, multiply the argument by 2. So sometimes I'll say function should have been written this way. Instead of x, they should have said, f is a function that takes the argument and does these things. But I don't know. I kind of like the idea of having x. So what does g do, right? It takes the argument, multiplies it by 3, and adds 1. Better known as 3x plus 1. All right. So once we know what g is, we're going to take this argument, square it, multiply it by 2, and subtract 5. Pretty straightforward from there. But what I was saying is, if there's an x here, that kind of means there might be a few exceptions, but it kind of means there's going to be I don't think there are very many exceptions. There's going to be an x in the final answer. So, in other words, you stop when you get a formula, and that's the formula we get. All right, now, almost always, if there's a part A, f of g of x, there'll be a part B, g of f of x, or GOF. Sort of. Wrong size O, but all right. So what's that saying? G of f of x. This is now the argument. And then what does g say to do? I think I see a typo here. What does g say to do? Oh, no. There is a typo. Maybe you can see it. G says to take the argument, multiply it by 3, and add 1. So a little square shouldn't be there. Take the argument, multiply it by 3, and add 1. Well, fortunately for us, they didn't square it. They didn't follow through with that typo. Distribute the 3. Combine like terms. All right. So f of g of f of x, given these two functions, is this. So we just found the composition of the functions, the composite or the composition of the functions, and we got a function. So what's this part about domain? So domain, just look. Are there any restrictions, legitimate mathematical restrictions as I walk through this? In other words, are there any x's that I can't square? Any numbers I can't square? Any numbers I can't multiply by 2? No. The domain of this is going to be all real numbers because at no point was there a problem with that. All right, so this is certainly a more interesting question. We're going to find fog. And f is 1 over the argument plus 4, and g is 4 over the argument minus 3. And that's our instruction. So they kind of start in with the domain. I don't really know that I believe when doing that. Let's actually do the problem. Assume they did do the problem. They're just finding the domain. Let's not do it that way. All right. Let's find it. All right. So the most abbreviated way they could ask the question is, first they give you the functions, then they ask you for fog, which you would write as f of g of x, which would be this. Now, right this second, I would say, you know what? X cannot equal 2. I might not write it here, but I just kind of keep track. X cannot equal 2. Why? Because if it were on this step, I'd be taking f of something undefined. So as soon as you see that, keep track. All right. Now what does f tell me to do, right? 1 over the argument plus 3. So it's 1 over the argument plus 3. Clear that fraction, and you get this step, this step, this step, and looks like we're almost done, but keep in mind, we know that x cannot equal 2, and if we look here, what else do we notice? X cannot equal 1. And that was true, well, actually that was true, well, here as well, but anyhow, recognize what would cause division by 0. And this is pretty common where, you know, the restriction that you found at the end is still obvious, still visible, still there, but the restriction I found earlier, the one about x not equaling 2, is no longer obvious. I mean, if I just looked at this, I wouldn't think 2 would be a problem. Sure, it would give you 0 in the numerator, but that's okay. This would not give you an error in your calculator. And neither would this, neither would this. Well, actually, it looks like this one might. Nope, it wouldn't actually, yeah. But back over here, it would give you an error in your calculator. So we want to avoid or exclude any number that would give us an error in our calculator. And so that's what we were doing. Let's see. Get back to where we were. All right. So, so it's just confirmation of what the domain is. Now, by the way, it's not what it started out to be. So let's see. Look at f of x. F of x, if they ask you for the domain of f of x, you'd say, oh, x is not equal to -3. And if you ask for the domain of g of x, you'd say f is not equal to, or x, is not equal to 2. This one carried along, but this one didn't. So it's a little hard to predict, but you could try to predict what the domain's going to be, but I don't see a purpose for that. Just run through the calculation, and you'll see it. Nice that it confirmed it later in the process, but I don't believe in looking for the domain at a separate time. Find it while you're finding the function. Okay, f of f, pretty straightforward. F of f, do what it says. At this moment, I notice, we're going to kind of keep a running tab, that x cannot equal -3, because it would give me an error right there. Continue the calculation, and notice what this would give you. I want to make sure that this is not equal to 0, and it looks like I'd get negative 10 over 3. No way I could have predicted that just because I did, function over function, but, it's obvious. I want this not to be 0, and so I solved that. And nice to see they confirmed it. All right. Looks like they were just kind of going through the motions again there. All right. Example 5. All right, so this one is actually going to show us a very special relationship two functions can have. It's not immediately obvious, but this function and this function are inverses. And inverses are functions that cancel each other out. And so, a famous inverse might be if I say, think of a number, take the cube root and cube it. Those will cancel each other and I'll just be left with x. Think of a number, well, the whole reason why we're here in this section, a to the x, and take log base a of that. Well, those will cancel and I'm just going to get x. You could even do this with take a number, x, subtract 2, and add 2. Well, those cancel, and you're just going to get x. These are all examples of inverse functions. The idea of a function that cancels another function. So back over here, if I called one of the functions f of x equals x cubed, the inverse of it would be cube root of x. And the amazing thing is students have a very good intuitive understanding of inverses when there's one operation. If you're adding, or you know the inverse is subtracting. When you're doing, cube root, the inverse is cubing. But when they have two functions, and I shouldn't say students, I should say it's challenging when you have two functions. I don't mean two functions here, I mean two operations. Here I'm multiplying by 2 and I'm subtracting 5. It's no surprise that the inverse of that function is going to be, instead of multiplying by 2, dividing by 2, and instead of subtracting 5, adding 5. The inverse is very predictable. What's not predictable is the order. I don't know how many, in other words, a lot of students will look at this and think, okay, I'm going to divide x by 2 and I'm going to add 5. And that is not this. Here I'd be dividing first and then adding 5. Turns out I add 5 according to rules of operation. Add 5 and then divide by 2. All right, but the point is, you could probably kind of spot that something special is going on here. And if you run f of g of x, you'll just get x. That is what I call a bingo moment, meaning you discovered something when you do this. What you discovered, and the wording of it, is that these are inverse functions. But that's more a topic of next section. But all right. Well, it turns out if they cancel in one direction and give you x, they're also going to cancel in the other direction and give you x. So you get this conclusion. Again, normally fog is not equal to Goff. You usually get totally different answers, but when they gives you the same, when they're equal, it'll be x. It will mean that they cancel each other, and you're just left with x. I'm getting ahead of myself because next section is about inverse functions, but they're obviously planting the seed. All right, so they're saying, hey, look at this. Could you think of this as two separate functions? In other words, could you think of this as one function that has you take the argument and raise it to the 21, and another function that has you take the argument, square it, multiply by 3, subtract 5. All right, so they're saying, get used to the idea of taking this and seeing it as the composition of two functions, where the outside function is argument to the 21st power, and the inside function is 3 times the argument squared minus 5. So that's really it. They're saying, look at this, identify the functions, outside function, and the inside function. This is it's an important idea in higher math classes like calculus, but for the most part, it's pretty straightforward what they're asking you to do. No, same thing. They give you this h of x, and they say, hey, wait, let's see if you can do this. All right. So make the outside function 1 over the argument, and make the inside function this denominator. And if you do that, you can start this chain that leads to 1 over x cubed, 1 over x plus 3, with two, I don't know, simpler functions, 1 over x and x plus 3. I can't really think of anything I want to add to this idea, this, this section. But section 6.1, composition of functions, the only thing I'll add is it did, kind of brush by the idea of inverse functions, kind of because that's why it's here. In other words, if they just wanted to talk about composition of functions, they would have put this in chapter 2. There really wasn't anything really astounding here, but they packaged it with exponents and logarithms because they have a lesson involved that uses this idea. But that's section 6.1. Should be able to answer any of the 6.1 questions just based on what we saw here.